Hi, everyone. Welcome to Bay Coding Club webinar for today's topic. Today's speaker is Larry Jing, and today's topic is how to engineer life, one project at one time. So before Larry began with his speak, let me introduce a little bit about what is Bay Coding Club, what Bay Coding Club provide. Actually, Bay Coding Club is a K-12 education academy at at Bay Area, California. We provide a K-12 about the cutting edge of computer science and mathematics. We offer different kinds of computer science classes, either online or offline. We have on-site places located at the Cupertino. And our course, not limited in program languages in computer science. We also have Roblox, such as Roblox Scratch, 2D Pie game designs, courses online, either on site. And we also have the robotics club, all the robotics online course. And at the same time, we have a lot of competition courses such as USICO, AP, computer science, ACSL, a lot of courses for older kids, for bigger kids, such as they went to the middle school or high schools. And our team, including our teachers, came from different such as big companies or the different universities, including some of engineers from big companies like Google, Apple, located at the Silicon Valley. Also, we have some of other teachers came from Stanford and MIT University. Their majors in computer science. And we provide our course only right now in English. We don't have any Chinese classes, but we're about to open Chinese class maybe in the future. So keep. Okay, this is the roadmap of Bay Coding Club development. We established in 2015. Right now it's about 6 years. This is a little bit about myself. My name is Ruby San. I'm the founder and CEO of Bay Coding Club. I'm a computer science teacher at the community for 5 years already. And I'm a mom with a 10-year-old daughter. And I worked in the information technology field for more than 20 years. So here are some of our examples of our courses, so which you can trace this online, our website at baycodingclub.com. We have a dynamic of our courses online provided in this fall 2021. Okay, this is also the snap pictures from our website. So we have Python, Minecraft, web design, Scratch, Pygame, Roblox, Java, JavaScript, HTML, robotics, USICO, AP Computer Science for high school students. And we also have ACSL, American Computer Science League. We provide our courses online with group classes or semi-private class or one-on-one. The group class means there are going to be 8 students in one class and one teacher. Semi-private, that means one teacher with 2 or 4 students. And one-on-one, of course, is just one teacher and one student. You can choose. Before you choose, you can do the evaluation just to let our staff know where you want to go and where your purpose to learn the coding. And here is one of the pathways that we designed for one of our students who want to attend AP Computer Science at high school. So you also can let us know your aims, your destinations to learn the coding, so we can design the pathways for you. And also here has some of the other pathways that we designed for the kids who like game design or artful design or the web designs or software engineer. And we also have this year we have ACSL. And last year we won the gold medal and silver medal for our students, and we also had won the first place of the national wide. And here's some of informations about ACSL. We have a team this year. We have an elementary team, which means if you're elementary school students, you want to attend ACSL online, and you can just register on our website. And also we have the junior team, which means if you are a sixth grader, you can join our junior team. We have a training course, no worries if you have no basic of any of the computer science levels. All right. Yes, this year we are gonna open our clubs. We have a lot of clubs, including game design club, Python club, and robotics club. Only $10 per week, or to 18 per week. You can just trace the information on our website at baycodingclub.com. This is our contact information. You can shoot us email at info@baycodingclub.com, or so you can call us at this number. And this is pretty much all that I introduce Bay Coding Club. I think I can give the time to Larry. So, hey, Larry, you ready? You can share your screen.
All right, cool. Hi, everybody. My name is Larry, and I'm going to go ahead and share my screen now.
Oh, yeah, by the way, I want to introduce a little bit about Larry. Larry is the excellent teacher at Bay Coding Club. He teach a lot of courses at Bay Coding Club. I will just give the time to let himself introduce.
Yeah, sure thing. So yeah, as Ruby said, my name is Larry. I'm a Python teacher here at BCC, and I'm also studying computer science at the University of Washington right now. And today I'm going to be presenting a little bit about learning the engineering process and learning how to apply it within your life. So I work on a ton of engineering projects myself, which I'll be showcasing some of them today. And today I kind of want to discuss how you can work on your own projects, because being able to apply this engineering process into your own life is a great way to just make your life better in multiple facets. So now I guess we'll begin by just introducing some of the projects that I've worked on, because I think they're cool, and I think it would be a good opportunity to talk about these things right now. So really, I began my engineering adventure with model rocketry. I actually joined a model rocketry competition in middle school, and basically the competition, which is called the American Rocketry Challenge, had to do with launching model rockets and designing model rockets and creating them. And the rockets have to go to a certain height, and they have to carry a payload of raw eggs, which must not crack. So it's a little bit like a egg drop contest on steroids. And so that was a really fun experience. And I think it was a good opportunity for me to learn a little bit about this engineering process, which I will be talking about in this presentation. And so because I enjoyed this so much, I spent a very significant amount of time working on this club with my peers in middle school. And I guess this is the part of the presentation where I get to brag a little bit, but we actually ended up winning the national and international championships of that competition. So for a brief moment in 2016, I was the designer and creator of the world's best model rocket. Which is a fun fact. And if you ever are in Seattle, you can go to the Museum of Flight in Seattle and check out that rocket, which won. There's me as a child standing next to my rocket in the museum. So that was a really fun experience, and I really hope that people can have experiences like these to get interested in engineering, which I'm very fortunate. And afterwards, winning this competition, I grew a little bit ambitious, and I kind of wanted to see some new heights in rocketry with this competition. So you can see that this rocket is like a pretty basic rocket. We make them out of wood and cardboard and plastic. But the following year, I designed with my friend this, which is an Arduino-based rocket stabilization system. So you can see that these are fins basically that can tilt, and the idea is that the rocket would be stabilized using these actuated fins, and they would launch up to a certain height, and then the fins would tilt, so that way the rockets always get the perfect height no matter what, by tilting the fins at the right time. And so this was like a multiple month wake up at 6 a.m. and work on this project kind of deal. And it took so much effort to build this machine. Uh, and so this rocket, it launched up perfectly straight. And then about 1 second later, it looked like this, which is not what you want to see with a model rocket. Although I guess that's pretty much the best you can expect when a middle schooler makes a guided missile. So that is probably one of the most outrageous failures that I've had in my engineering career. But it was a wonderful experience to learn more about some of these skills that we'll be talking about. And I wasn't finished there. I also created this thing throughout my time with rocketry. So I'm not sure if you guys will recognize this, but basically, you might notice that the rockets before, like those model rockets, had fins, but this is a real rocket. And you might notice that it doesn't have any fins. So normally fins are what keep a rocket flying straight and stable. So before, that machine that I made had tilted those fins, and it would try to keep it stable. But these real rockets that you see launching by NASA and SpaceX and all these aerospace companies, they don't have any fins. And the reason why that is because they actually have something at the bottom called a thrust vectoring control system, which basically tilts those engines below the rocket and kind of directs the thrust in a different direction that allows the rocket to keep pointing perfectly straight up. And that was my kind of new idea for how I would stabilize these rockets and make them far more advanced and over engineered than they needed to be. And I ended up making that. So I believe this was early last year when I worked on this project. And well, this is in slow motion, so it looks a little bit goofy, but you can see the rocket motor is being tilted up and down, uh, left and right, and you can combine those motions in different ways to kind of tilt the rocket in every direction. So now it's tilting diagonally, and it can move in circles. And so yeah, this was just another one of these projects that I spent a lot of time working on, and was a really great experience. I believe at the end it has a little explosion here as the yep, there it is. Uh, so yeah, moving on. This is a project that I worked on early in 2019, 2020. And it goes like this. So maybe things are a little bit different nowadays now that school is almost always online, but imagine you're walking into a classroom and the teacher needs to take attendance, and that can be sometimes a pretty significant hassle. Like maybe the students are not in their desk, not sitting down in their seats. Some students are like running around, jumping around, and some students maybe they went to the bathroom. So when the teacher is trying to take attendance at the beginning of class, I feel like that can be a lot more complicated than it needs to be. So what I imagined was, what if we had this system where at the beginning of class you just walk in and you could scan your fingerprint, and then on the computer screen of the for the teacher's computer, they'd just see like who's in the classroom, who's not in the classroom, who's absent. And by having the system, we're able to just really streamline and simplify this attendance process that can sometimes take whole minutes, which is outrageous, I think. So that was kind of the vision for this project that I was working on, and over and through working on this in a class in my school with a partner, we actually made this project into a reality. And so we made the hardware and the software for this project, and we like kind of integrated it into the classroom, and we tried it out. And we will talk a little bit about that later in this presentation. But here you can see this was at a computer science fair where Microsoft actually invited us to present this project at their Teals Computer Science Fair early last year. And we kind of showcased a lot of the things that we worked on, trying to solve the problem of unruly attendance. And lastly, I create a lot of things just for fun sometimes. So this is something that I saw like probably just on the internet one day. And it's basically just it's like a table full of sand, and there's a metal ball that rolls around and traces all these intricate patterns. And I just think there's something satisfying and beautiful about a machine that traces these patterns and erases the things that it draws, and it's retracing them, and it's just keep making these patterns every single day, um, again and again. And it's like retracing them and redrawing them. It's just immensely satisfying to me, and I thought that was so cool when I saw it on the internet, until I found out that it was about $8,000. And so, I mean, I don't have that kind of money to spend, so I just made my own. And that's kind of the essence of engineering. When you want something and when you need something, um, it's really up to you to make it into a reality yourself. And I think that a lot of people, they have the capacity to do things, but they don't realize it. Like they think like, oh, it's too difficult, or it's too complicated, or it's not worth it. But really, this presentation hopefully is going to show you that working on your own engineering projects is a worthwhile investment, and hopefully it's something that you can be interested in. If you're interested in this kind of creating these sand table things, you might want to check out Bay Coding Club's computer science and robotics classes, because I think that they're a great introduction to learning about the skills that you need to create something like this. And if you're interested in this one specifically, you can also go ahead and check out this video that I made, because I go in really in depth into a lot of the engineering design process and all of the failures and triumphs that you go through when you create a large scale project like this. So I'll just drop that link in the chat if you're interested. So let's talk about the actual process that you kind of want to follow when you're creating an engineering project, such as any of those that I mentioned before. And the first step is always the same. We want to locate a problem. And the idea with this is engineering is basically just problem solving. And this, it seems like a really simple step because there's problems everywhere in our life. But the hard part is actually knowing that there's a problem and knowing that there's a solution somewhere in the ether that you have to kind of pull out of your mind. Because people, like I like to complain about all these things that I see in my life that are difficult or annoying or boring, and making that leap from knowing that there's a thing that bothers you to actually finding a solution and creating that solution to it, it can be a pretty big leap at times. So the first step is to be finding this problem and understanding it really well. And when you're trying to define the problem that you want to solve, I think it's helpful to kind of ask yourself these three questions. Like, who does the problem affect? Is it a global problem, something that is impacting the world, or is it something that's just affecting me personally within my own life? Like both of those are valid, but because, we obviously want to solve problems that are affecting the world negatively, but we do want to solve problems within our own life too. But just knowing which one it is helps you narrow down your approach to actually solving the problem. And of course, why is it important to find a solution in the first place? Is this problem valid? Like, is this a problem that I can avoid, or is it a problem that I need to find a solution to? Why is it important to find the solution? And what are we going to need to do, and what limitations do we have? That's just kind of formulating an understanding of the accomplishments that you need to accomplish, and also the limitations that you're going to need to forego when you're actually trying to solve this problem. So this this image here shows a high-rise building on fire. So this is the particularly infamous case of Grenfell Tower in the UK. So just a little bit of background. In the, I think summer of 2017, there was a small flat on the fourth floor of this building that caught fire. And the fire spread to the entire floor before firefighters could even reach the building. And the fire was spreading upwards across the entire building. And in less than 45 minutes, the entire building from the fourth floor up was just in flames. And firefighters' hoses can't reach any higher than the fourth floor since you're having a hose from the ground. And so tragically, this fire actually resulted in the deaths of over 70 people and £1 billion of economic damage. So it's crazy to me that over 14,000 fires just like this one happen every single year. Um, yeah, and so we've identified that this is like a horribly tragic situation, but I think that we need to go one step further and actually identify some of the root causes of these problems. So, like looking at this situation, I think one of the clearest issues with firefighting is a lack of accessibility, maybe, to the source of the fire. So, hose and the water jet technology, it's all dependent on road-based fire vehicles. So that's limited in its reach. And these are technologies that have been virtually unchanged for hundreds of years. And the second problem with these kind of outdated methods of firefighting is response time. So firefighters and EMTs, they're trained professionals that are really effective on the scene, but oftentimes they don't have a way of knowing where the problems are until they're actually notified of them, like somebody calls 911. And this can take longer than it should. So this was kind of the initiative for a project that I was working on called Firefly, where we would look into how we can more effectively and efficiently combat these fires that happen in high-rise buildings. Um, so my team and I envisioned, like, what if we could have temperature sensors and smoke sensors scattered all throughout a building? As soon as there's a fire, the emergency personnel would know about it instantly, and uh, and to fight the fires, to kind of try to solve this accessibility issue, you could have swarms of drones or autonomous drones that would kind of survey the scene and record important information to allow firefighters to have this eye in the sky. And moreover, they would be able to combat the fire if they had some kind of basic fire extinguishing system that would allow them to combat the fire in swarms. So that was kind of the initiative or the mission statement with this project that we're working on. And we will try to talk about it a little bit later in this presentation. So, I mean, I guess to wrap this slide up, in every sense of the word, this is a problem, and it's something that we want to solve because of how big of an issue is. And that's an example of one of the problems that you can pick for engineering. But on the other side of things, this right here is also a problem. Uh, Me forgetting to feed my fish every once in a while, that is a problem. And this just goes to show you that the problems that you solve for engineering can have hugely wide scopes and in terms of how different they are. Like, this is just something that affects me in my life, but I'm sure that other people are also affected by the same problem. Like, maybe you're going on vacation for a week and you need a way to feed your fish. That is a location where you can apply engineering skills to fix that problem, like we're going to be talking about. So, can anybody think of a problem within their life that you think engineering could be a solution to solve? You can go ahead and just unmute yourself. Anyone at all?
Drawing perfect circles.
Okay, yeah, that's interesting. So, yeah, that's, I guess, if you're that's an example of a problem. It can be as little as wanting to draw perfect circles. So maybe imagine you are an artist and you draw a lot of circles, and that is one area where you can apply engineering to create a solution. It's the possibilities are literally limitless. So the next step after finding a problem is to begin brainstorming. And there's more to this than it seems, but brainstorming is basically just trying to find some possible solutions, and formulating these ideas before you go ahead and actually create them. So there are a couple of things that I want you guys to keep in mind when you're doing your brainstorming, which is first, we need to be establishing our goals and constraints always. So before you begin brainstorming any possible solutions, make sure you have like a clear understanding of your limitations and what you need to accomplish, right? And this kind of ties in with what we were saying earlier about defining what the actual problem is. It's also important to explore possible ideas. So thinking about different ways to solve the problems and ways to put these ideas into action, this is kind of the core of what brainstorming is. And lastly, I think it's really underrated for people to think outside of the box, because creating these solutions, these alternative solutions, it's really important to think about those when you're creating things, because oftentimes that'll be the reason why a solution doesn't already exist. It's just that it's so like fresh and new that it doesn't already exist, and you can be the first person to bring that into reality. And the next step, which I think kind of ties in with brainstorming, is definitely researching. And this is quite important because oftentimes we don't have enough in our own brains to come up with the perfect solution. And other people and other resources online or on books are very knowledgeable about all sorts of topics. So it's a good way to apply yourself and use that information to our advantage. Like it's possible that a solution to the problem already exists, and you can kind of use that for inspiration or for information to when you're creating your own solution to the problem that you're trying to solve. So going back to that like firefighting initiative that we were working on with my friends, that was an example of where research came in really handy. We found a lot of information on books and online, and we even spoke to the CTO of a drone startup that is here in the University of Washington incubator that we spoke to about using autonomous drone technology. And so knowledgeable people like that can be really helpful when you're working on projects that are kind of tangentially similar to what they're working on, because the information that they have inside of them can be really helpful for your own project. And I think once you've kind of brainstormed what your idea is and formulated a lot of research, you can start beginning the one of my favorite parts of the engineering process, which is prototyping. And for those of you that don't know, prototyping basically just means creating an initial version of the product or project that you're working on. So there's kind of three major phases of prototyping. And it begins with designing. So you need to begin with planning out your ideas beforehand before you just start putting stuff together. And so I think every good prototype begins with a good design, like planning out these ideas beforehand, allow you to have a solid record of your thought process. So later when you're evaluating, step 3, you can look back on your notes, and that way you can kind of judge what works and what doesn't work. The next step is to create things, which is basically kind of the essence of prototyping, where we're putting stuff together and actually making a thing. And although this is pretty straightforward, I guess it is important to note that we do want to follow our procedure or our plan as closely as possible. And any impromptu changes that are kind of on the fly, you should note those down as well. Just making sure you maintain this organized structure to your prototyping process, which I find important personally, because when we're evaluating, we reach kind of the core point of prototyping. That'll be really, really helpful. So the entire point of prototyping really is to fail fast and learn from your mistakes. And I say the word fail, but really when you're prototyping, there's no failure. And I mean that literally. I guess the only failure is if you give up and stop prototyping. But really, when things go wrong when you're prototyping, that's actually considered a success, because the whole point of prototyping is to know where things go wrong. And that way we can fix them with the next iteration of our prototype. So here is the initial concept that I had with the Firefly kind of firefighting drone. You can see that this is early in the prototyping process. We're just kind of creating designs and throwing them out on paper. And this is an initial concept render. You can see it has some thermal imaging sensors on the front that allow the drone to kind of see into the fire, which was the idea. And below the drone, there's kind of this fire extinguishing system. And the idea is that it would allow the drone to combat small fires and large fires and swarms. But when you're prototyping, the initial creation should probably look a little bit more like this, where we're creating this basic prototype to test small parts of the functionality before we move on to these larger, more fully fledged ideas. So this was the prototype that we were using to do our testing when we were working on this project. And as you can see, it's a lot more basic. We made this basically to test out our software and our sensor suite. And I can showcase this a little bit later in the presentation if we have time, but this is more of just testing these basic features before we move on to a more fully fledged product. And this was actually something that we did make. You'll notice that it's just made out of aluminum C-channel and some basic like 3D printed plastic parts. And so that brings us to some of the qualities of a good prototype are that they are functional because, well, clearly a prototype should, we're trying to validate the functionality, seeing if it actually works. So you need to have a prototype be functional, but kind of more than that is a prototype should not be too difficult to work with or to make. So prototypes are often made of materials that are really cheap or easy to work with or easy to access. And that allows you to rapidly iterate and test different things when you're working on your projects. Because we're going to be making so many iterations and versions of our different projects that this is enough that this is an important part of prototyping. We kind of want to make stuff out of cheap and easy to work with materials. And this is just a quote I like from Thomas Edison, inventor of the light bulb. And it just goes to show you that, again, failure in prototyping is really subjective. Like because the whole point is to find these failure points or to find the points where the prototype is not working. That is there really is no failure. It's just we're counting that as a success when we're prototyping. So when things go wrong, which I guarantee you they will, it's important not to get discouraged. Like when my rocket did a U-turn in the air and crashed into the ground and almost killed a dog, that was not a failure. That was just a way that did not work. And I think back to that sometimes, and that'll make you feel better when you're feeling discouraged. This is a table that I like to use when I'm judging different ideas or prototypes. And sometimes it can be hard to pick between different ideas when you have a couple of ideas and you want to kind of find out which one's the best. And so I think this might be helpful for you guys. So if you want to put your ideas, you can put them in the columns here in the table, and the attributes can go horizontally in these rows. And then you can kind of score them on each attribute. So let's say like idea A is really good for attribute number 1. So that scores a 10, but it's like not very good for attribute number 2. So it scores a 3. And basically you can go through and score all of your ideas in this manner. And when you're done, you can kind of sum things up here. So like if you add up all these numbers for column A, for idea A, you get 20. So idea A gets like a score overall of 20. Idea B, if you add them up, it gets a score of 19, I think, and idea C will get a score of 24. So basically you're wanting to use this overall score to kind of get us an objective idea of which one is better overall. And you can use that to help guide your decision-making process. So I can look at this and say like, okay, idea C has like the best overall score. So I might try idea C first, and then I'll try idea A, and then I'll try idea B in that order, based off of those kind of overall subjective scores. And another way that this is helpful is that it can kind of tell you different ways that it can kind of help you formulate a new idea based off of how each thing does different things well. Maybe I can make an idea D afterwards that kind of draws the best components of each idea. Like, for example, idea A is really good for attribute 1. I might take the part of idea A that makes it good for attribute 1, and I combine it with the parts of idea C that make it good for attributes 2 and 3. And then I can come up with like a new idea that is much better overall. So after you've kind of gone through this prototyping process, you want to be refining your design, which kind of ties in with the evaluation step. Because once you evaluate how well your prototype is, then it's time to make those changes to kind of make it better, just one step better. And I think the prototyping step and this refining step kind of go in a cycle. It's something that you want to repeat in a cycle again and again, where we're prototyping and then we're refining our design, we're prototyping and we're refining our design and making it better and better. So that fingerprinting process, fingerprint attendance system that I was telling you guys about earlier, in its early stages, it looked like this. So you can see it's literally just in a cardboard box with the electronics just kind of jammed in there with all the wires everywhere. And this kind of brings us back to what we were talking about with creating prototypes that have easy to use materials, really accessible and iterable materials that are easy to work with. And so that's a good example of prototyping using these really basic components. And we were able to kind of write a lot of the core software functionality and integrate a lot of the hardware just as in this state, like in a little cardboard box. And eventually, of course, we created the plastic shell for it and made the design a little bit more refined. But you can see it's basically like the same software that's running, because we're able to use this prototyping process and create all the basic necessities of it. And then when we're refining it, we can kind of make the small aesthetic details a little bit better. Yep, and as you can see, here's a demonstration of it working. This is a person named Brady scanned his fingerprint, and it says, "Welcome, Brady." Oh, right, and the software that we wrote on the computer also follows the same process. So this is just here to show you that when you have kind of large software projects like you might be working on in your BCC classes in the future, you're also going to be following a version of this engineering design process where you're creating basic versions of it, and then you're refining them, and then you're creating basic versions, and then you're refining them. These prototypes kind of get better and better and better until you end up at your final iteration of it. And what a lot of that means, like, we're creating the core functionality of something before we work on the small like aesthetic details. So like maybe I'm making that application to show like the attendance of all the students that are in the class and all the students that are not in the class. We begin with just like having a list of names, and afterwards, like as we work on it more and more with each prototype, then we can start adding the details, like, oh, we'll add a scroll bar here and some buttons here, add some color into the thing. So all of those small details we work on after the core functionality of the prototype, because after all, the whole point is to get a basic thing working with what is called in the industry a minimum viable product, or like the basic core thing that is able to work. So when you're refining, I guess it's important to kind of imagine what the next step of your prototype should look like. And just like before, that should involve understanding what works well and what doesn't work well, and how we can make that prototype better. And once you follow that step again and again and again and again, eventually you will have made something. And that is kind of the essence of engineering, where you're kind of following this 5-step process in order to create something of your own will, kind of draw it out of your mind. So a little bit of recap here. Can somebody tell me what the very first step of the engineering process is? Anyone brave enough to go ahead and unmute and let me know? And I know a lot of you, some of you might have joined in late, so maybe you missed it. Okay, I guess nobody remembers. So don't worry, guys. I'll tell you. The first step of the prototyping process, of the engineering design process, is to locate a problem. And kind of connecting off of that, anyone know the second step of the design process? It starts with B. Starts with brain. It's a word that involves brain. Okay, somebody DM'd me saying brainstorm. That's exactly right. Um, so yeah, I mean, if you instead of messaging it to me on Zoom, you could have just unmuted and said it. But yes, brainstorming possible ideas is the next step of the engineering process because we this is this part where we're actually trying to find our ideas, and then kind of tied with that is doing the research to kind of pick an idea and see which one works. Does anyone know what step is next? I said it was my favorite step, and it starts with P. Come on, guys. Somebody please unmute and say. Okay, Sophia says prototyping. That is exactly right. Prototyping is our next step because after we've brainstormed those ideas and we've made our research and we've picked an idea, it's time to actually make our prototype. And obviously, connecting with that is refining the prototype because, as I said, there's kind of a cycle between steps 4 and 5 where we're making prototypes and making them better, and then going back to the drawing board and making another prototype and making it better. And finally, the last step is kind of presenting our project and having a finished product that we've made throughout this process. So a lot of people ask me, like, they're kind of confused about how to actually get started making things. And I understand, like, it can seem difficult. So I wanted to mention, like, some tools that I use to create things that I think might be helpful when you're creating things within your own life that, maybe you can learn about. And I guess the first thing I'll talk about is CAD, or computer aided design. And basically what that is software that allows you to make 3D models of something before you make it. And personally, I think that this is super important because oftentimes when you're working with these physical things, you're getting these ideas like out of your head and into reality. And being able to design a 3D model of that is really important. And some of these more complicated softwares will even give you more like useful information. Like some of them might tell you you can do like stress analysis on a component or something like that, or measure how much it's going to weigh. Having all that information is useful, but kind of the main reason why is because we want to have these solid like visual ideas of why we want to of what we want to make before we make it. And this kind of ties with having a 3D printer or a way to kind of make these things into reality really easily. So if you're interested in making more complicated projects, I think that a 3D printer is a worthwhile investment. And it is exactly that, an investment. I know that it can be quite expensive for people, but like in reality, I think that a 3D printer is more accessible than people realize. I think I built my own 3D printer for around $150 probably. And in those early days, I got a lot of use out of it, just kind of designing 3D models and then making them into reality to work on my projects. And so if you're interested in CAD, definitely go check out the Bay Coding Club CAD class, which is 3D modeling with Tinkercad. And Tinkercad and Fusion 360 are all really good free computer-aided design softwares that will allow you to create these basic 3D models. So if you join that 3D modeling with Tinkercad class, you can kind of get an idea of how to use CAD, and you'll be a lot better ahead when you're making your own projects. But if that's not for you, another alternative is just to draw things out with paper and pencil or a whiteboard. And so just getting your idea out of your head and onto paper is just a great way to start something because not only will you have a better idea of what you're doing once you get it onto paper, you'll also have a record of what you were thinking because you now have that sheet of paper that you can follow. I make a lot of my projects, at least in the early days, out of cardboard and Legos because they're just really easy to use to put things together and they're intuitive and easy and abundant. So cardboard, like you can see, I use that with my fingerprint scanner. That's just a good prototyping material. Even something like Legos, like people have Legos just hanging around in their room. Those are also good things that you can use to create things if you don't have access to a 3D printer or something like that. And last but not least, the electronics are all handled, for my projects at least, a lot of them are handled by Arduino or Raspberry Pi like microcontrollers. And what these are basically like mini computers. I actually have a couple on my desks. I don't know if you can see on the camera, but these are all just like kind of mini boards that you can use to write software and they can control electronics to handle all the functionality of whatever project you're working on. So the project that I just held up here, this right here is a fish feeder. So remember I said I had a problem with forgetting to feed my fish. And this is a way that I'm working on right now to solve it. And so if you're interested in kind of the electronics side of things, projects that have kind of an electronics component or a coding component, look into using Arduinos because I think that they're quite easy to get started in and they're really, really helpful when you're creating all sorts of things. And when you code an Arduino, that's coding it in kind of a version of C++. But I noticed that it's like pretty much, for those of you that are unfamiliar, it's pretty much really similar to Java. It has a lot of the same syntax and stuff. So, if you're not familiar with that, don't worry. Many of you take Java classes here at BCC, or if you're interested, you can take Java classes. And that'll allow you to get the basic like understanding of coding concepts that you will need if you want to go that route with Arduino. Yeah, so finally, I thought we would just do a little bit of a Q&A here. We have about 12 minutes left, I think. So yeah, now we'll open it up to questions. So if anyone has any questions, feel free to ask them now, because now is the time for it. And if you're uncomfortable asking questions in the call, go ahead and you can message them to me in chat as well. Anyone have any questions?
Well, Larry, when we collect the registration form, we do get some of the questions after you ask the question from here, right? Okay. Yeah, we can see if anyone has questions in the Zoom or at the Clubhouse. Anyone, if you have any questions, just raise up your hands and let me know. Or in the Zoom, you can open your Mac and go straight to ask Larry.
Yeah, definitely. I'm happy to answer any questions about the process, the engineering process we just talked about, or just like questions in general about, I don't know, projects that I've worked on, because there are a ton, and stuff like that. I actually worked on so many projects that when I was creating this PowerPoint, I had way too many things to put in here. Otherwise, we'd run out of time. So if nobody has any questions, I guess we can always go through more projects that I've worked on, because I've added them at the bottom of this thing just to fill up time. Yeah, definitely send in me your questions. questions.
If nobody has questions, maybe you can pick one or two from the registration form that I brought up here, which is the first one. Some of the parents ask, notice the project and engineer. So maybe for the kids, they have no idea where to go if they really like to make like makers to do things, but they don't know how they can accumulate their strengths or knowledge. So what should a sixth grader and to learn? What kind of a language should learn? I believe this parents ask this kind of questions.
Okay, yeah, that's a great question. I'd be happy to answer that. So I think that at least for me personally, when I was interested in making these things, a lot of the things I'm actually kind of self-taught, where I'm just like tinkering with all these materials. But luckily, a lot of these resources exist online. Like you can learn pretty much all the coding concepts that you need right here at Bay Coding Club, or even just online, like just following along with projects online. And for the more hardware oriented, like physical stuff, like learning how to use CAD and learning this process, there are classes in a lot of schools that kind of teach these concepts. And if not, there are also clubs that you like to follow. So like I mentioned, Rocketry Club was one that I personally followed. I know a lot of people are into Robotics Club and stuff like that. Um, yeah, and I guess this would be a good time to bring up like the Bay Coding Club has their own robotics club coming up, like Ruby mentioned earlier in the presentation, and this would be a good way for students to kind of learn more about making things and tinkering. Um, I believe in the robotics class for BCC, we actually do Mindstorms, like Lego robotics, and this was something that I played with a lot when I was a kid. Probably when I was about 9 or 10 years old, I made a bunch of robots, and um, they they do have like kind of a block coding system where you program the robots, but it's not really like writing lines of code. It's just it's more kind of like Scratch, where you put in these blocks of code. Um, but actually creating the physical robot was also a good learning experience. Um, and that can be a platform for people that are interested in creating things but don't want to go into the hassle of needing to like design them in CAD and 3D print them somehow and stuff like that. So yeah, I hope that answers the question. Let's see, somebody else asked me a question in the chat about how does the Firefly drone basically not get burned by the fire if it's like a drone outside of the fire? That is a good question. And um, let's see, I think I have a picture here of the actual drone. Um, yeah, so this is our prototype drone, and here it is without the shell, but I'll just leave it on the screen as we talk. But our idea with this drone is that we did a lot of research. Like I said, that's one of the steps of brainstorming. But we did a lot of research into how to basically heat proof something that needs to be lightweight because it's on a drone, and also needs to be like really resilient to fire. And we ended up finding about this material created in like I believe the 1970s by just this hairdresser guy, Maurice Ward, who invented his own material called Starlight. And he was so secretive of his material because of its properties of protecting against fire. He was so secretive that he wouldn't tell anyone the formula for this material. And to this day, nobody has cracked that formula. But we kind of made our own version of that material where it is like almost heat proof, and it's really lightweight. So this kind of material that would prevent the drone from being burned. So the idea was we would coat any autonomous robot with that thin layer of that material, and it would prevent it from being burned.
All right, thank you, Larry. There's another student ask, how how do they get started, like embedded system? Yeah, maybe the main, is it possible for switch from software to the hardware part? So what the connection between each other?
Yeah, great question. So I think if you're unfamiliar with kind of the hardware components, Arduino is a great place to start, and also Raspberry Pi. So you can see this drone right here is based on Raspberry Pi, and you write all the code on there, and it has a shield, which is basically a board that you stack on top of the Pi that has all the hardware like the sensors and stuff. But Arduino is a really more basic platform because you can buy like the individual parts online, and they're if you just get like a kit or something, they have like all the individual sensors that you can learn to connect one by one on a breadboard. And just kind of learning to tinker with these is an important part of the learning like the electrical engineering side of things. And so Arduino would be a good platform. Raspberry Pi would be a good platform. Um, yeah, so looks like Ruby is now
Yeah.
screen sharing.
Yeah, I have the screen sharing about our robotics project, and also I want to mention a little bit about our Bay Coding Club, Raspberry Pi's Arduino's kits for I think most of the students are. Oh, we have to, yeah. We have the Arduino's case for K to 12 to learn a lot of things such as the solar cars, vacuum cleans, which inside is looks like your prototype or the original things here. So we have already made for case, and you can just open it up and to see what's inside of there and why it works, why it functions. So also you can buy from our website. Yeah.
Yeah,
And
absolutely. These kits are a great way to get started with these
yeah,
electronics.
case. And we also have on-site classes such as self-driving cars. So we have sensors of the cars, and they can make a lot of self-driving, like trees, uh, the road thing a lot. But because of the pandemic, we close all the on-site. But right now, kind of resume a little bit of a road. So yeah, join our on-site class at Cupertino only right now. All right, this is a part of yeah, back to you, Larry. Any other questions from chat or from the Clubhouse? Yeah, I didn't see anything from Clubhouse, but if you have from the chat, no, if you don't, you can yeah, I can stop sharing and you can go ahead with your project.
Okay, yeah, sure. Yeah, I have a few more slides that I can share if you guys are interested. Let's see. So this right here is an early prototype of my fish feeding project. So here you can see like it's just an Arduino, and it's got some like really basic parts, like it's got a transistor and a switch and a motor, and it just has this little auger that like contains the fish food, and when it spins, the screw pushes out the fish food into the tank. So uh, yeah, I don't know if you can see it from this 5-second video, but it's pushing out this fish food. And this is the earlier version of the one that I'm working on right now that I'm showing you guys. And the difference is that this one will have Wi-Fi like connectivity because I'm using a Wi-Fi connected board. Um, and my idea is that I want to go on my phone and be able to see like if the fish are fed, and I can manually feed them from my phone. And so that I think that's just another example, yet another example of the refinement process that we go through when we're creating prototypes like this one. Let's see. This right here is a project that I worked on. you can see it's a lot of soldering work. This is one of the more complicated electrical engineering projects, but this is another Arduino based board, and it's almost like a little phone. Like it has a display and a battery, and the idea of this is it displays inspirational quotes. So it connects to the Wi-Fi, and it you can press these buttons, and it'll give you some motivation throughout the day. And I think I also added some other features, like you can tell the time by holding down a certain button. So if you hold down this button, it'll tell you the time. Or it can do like a magic 8 ball, like help you make a decision. So here it says my reply is no. So like it's basically like if you're trying to flip a coin or something. And it can tell you the time and the date and stuff like that. And so yeah, that was just a cool project that I worked on last year. That involved a lot of engineering. I already showed you guys the Firefly drone here, but this was basically the prototype drone that we created at to test all of our sensors. Yeah, we actually presented this project at TEDx Youth at Redmond, I believe in 2019. So if you're interested in that, I think there's videos of that on my YouTube channel, so you can go look at that. Oh yeah, this is a pretty neat piece of software that I wrote in MATLAB. And I'm including this because this is just going to show you that the engineering process definitely can be applied into software engineering as well as actual hardware engineering. It's pretty much exactly the same. And so what's happening here is if you look at this picture on the left, it's like a picture that I took, I think in Banff, Canada, and it's very long, right? I want to post this to my Instagram or something, but it's too long. It takes up too much of the page, and I want to take up less of the page. But if I crop it from the bottom, then you don't get to see these lovely trees. And if I crop it from the top, you don't get to see these trees over here. So what I wrote is a seam carving algorithm that kind of detects the parts of the picture that you want to remove and the parts of the picture that you want to keep. And it's able to kind of shrink this picture without losing any of the parts of the picture that you actually want to keep. So you can see that this new image here on the right, it is shorter, but it still keeps the part of the picture that I want to keep. It just loses all the boring stuff in the middle that's just like plain white pixels that are just showing the lake water, but it's keeping all the interesting stuff like the color of the algae in the water and the trees and these trees in the background as well. And so this is solving a problem, right? The problem of me not being able to post this picture on my Instagram. And then the brainstorming involves, coming up with all these solutions, researching until I find an algorithm that might actually be useful in this situation. And then prototyping is like actually writing out the software and testing it out, working out all the bugs until we're able to do this. So yeah, that is a pretty neat example of applying this decision-making process to software engineering. Oh yeah, and so this huge hunk of metal is actually a rocket in its early stages. So now I'm not working on model rockets. Now I'm working on giant rockets that go to 30,000 feet in the air. And this is part of my school's Society of Advanced Rocket Propulsion. And we're just making this huge rocket. And I have the slide here just to show that things are much more involved when you're with like a big organization like this. And it helps to have things organized. Because for stuff like this, it tends to be a lot of people working on these mini projects, and you kind of put them all together and create one final project. So like for example, the final project here is the entire rocket, but I'm just working on a small part of it. Like I'm on the avionics software team. I'm working on the part that handles like live video streaming from the rocket. Another person might be handling like, I don't know, this gear right here, or somebody might be handling this valve right here. Like all of these individual parts have to come together. And so when you're working with a team, it's kind of a whole new set of rules that you need to follow by. And just for fun, I included this picture. This was a boat that I made with a couple of friends out of a bunch of bottles. Um, yeah, and I made this in middle school. This is I include this because oftentimes we make things just because it's fun and because we like it. And I hope that you guys now feel a little bit more confident making some things in your life. Because I mean, it is fun, and hopefully you can have some good experiences and some good things to come out of it. So yeah, that's pretty much all I had prepared. Thanks, everybody.
Wow, thank you, Larry. I really like the picture. The last picture you showed is really fun, I believe. So yeah, our Bay Coding Club slogan is just use your imagination combined with computer science, art, and artful design together, and to do some creativity things to use your technology to change the world. So it's just not only for learning programming things. The purpose, I think, in our life, it just find the meaningful of yourself and get started from the interest. Yeah, find your own potential and interest is really important. And our Big Coding Club really want you to show us your creativity with the technology. So, all right, I think, Larry, I don't know if anyone had the last comments or questions here today. I give you guys the last chance and to open your mic, or you just raise your hands up and go to the panel and to ask the questions to at the clubhouse. Okay. Anyone has any question, comments on today's topic? Yeah, I believe there has some questions from a registration form when the case register on today's webinar. So Larry, do you mind you answer some of questions again? Yeah, one of the parents asked when should a case get started from learning code? I mean computer coding, maybe, yeah. So yeah, I don't know if what you answer the question. I think it's no answer, but I maybe will listen to your answer. When do you think is a good year for kids to learn computer code? Or you can introduce yours. You muted, we cannot hear you.
Oh, sorry. Yeah. I think that this is a pretty difficult question because it really depends for everyone. And obviously, I think that like having learned a little bit of stuff myself, I think that as early as possible would be good. But it really comes down to like what the student is interested in, because I think it's unfortunate that a lot of people start learning code early in their lives, but because it's like not as interesting to them, they'll kind of formulate an opinion that's like, oh, I don't really like this. It's not fun or interesting, and because of that, they'll be more discouraged to kind of learn these really important skills later on. So I think it's not as easy as just saying starting your kids um, to learn coding as when they're really young. It's more about finding what their interest is and appealing to that using these skills that we're trying to build up. Me
Right.
personally, I didn't really learn any code until I took AP Computer Science. That was only probably 3 or 4 years ago, in my junior year of high school. So yeah, it's never too late to get started, kids.
Right. Yeah. Never too late to get started. Yeah. So, before you take any AP Computer Science, have you ever learned some of the hardware part like Lego, robotics, Arduinos, or Raspberry Pis before?
Uh-huh. Yeah. So when I was like a kid, I played a lot with Mindstorm's Legos, which is the kind that I believe you use in the robotics classes here at BCC. Obviously, it's like an older generation, but
Oh,
those were kind of my introduction into the hardware side of things. But all of the Arduino stuff for me, at least it didn't really come until I was more familiar with the coding concepts because you do need to code Arduino and Raspberry Pi to work with these electronics. On the other side, I did do a lot of rocketry in middle school, like I said. So that was kind of my introduction into learning the
Okay.
how to make things.
All right. Yeah. Yeah. Keep the interest in you. It's really important, I believe. Yeah. So yeah, the students who are really who really think you're interested in any robotic class or club at Bay Coding Club, you can just log on our website at baycodingclub.com and to look at it. We're open our Bay Coding Club at the end of September, and the normal robotic class will open soon. And we do. We also have some of other clubs, such as game designs. Yeah, there's a lot. Yeah, just log on our website or call us or just shoot us email. I believe pretty much all for today's presentation and webinar for all of the questions. I believe Larry has wrapped it up. Is any takeaways from today, Larry, for the last minute for the comments?
Okay. Yeah, so I guess the takeaway is okay, Steve Jobs once said that the creation of everything that people have made is like a mountain where everyone is just adding their own layer to the creation of like technology and the advancement of technology. And I think that people are just adding their own layers to this mountain, and sometimes we don't see like all the technology that's underneath your current layer. But it's up to us to all be adding our own layers and building this mountain higher and higher, one pebble at a time. And the way by doing that is by making the world a better place through engineering and applying your creativity and your imagination to find a solution to all these problems that we're facing in our life. So everyone should spend more time thinking of problems in their lives and solving them, and then the world becomes a better place. So go forth and do that.
All right, thank you, Larry. Wow, thanks. Yeah, keep finding the problem and keep finding the ways that you can solve it. Okay, to make the world is a better place that we can live. Thank you so much, Larry, for today's webinar. And we also have another webinar for the next week. Just stay tuned with us and just get involved with our Bay Coding Club community. Let us know if you have any questions and you want to solve any problem that you can find in your world. Okay, all right. Thank you, Larry. I think pretty much all for today. And thank you all for being showed up on the Zoom or on the Clubhouse. Okay, thank you. We're gonna leave for today. Take care.
Great. Thank you everyone for showing up.